A soft, unmistakable reddish glow pulses steadily from the shoulder of the constellation Orion, glowing faintly yet unmistakably against the backdrop of the night sky. This glow belongs to one of the most famous stars in the heavens, Betelgeuse. Betelgeuse, one of the most iconic stars visible in our night sky, has long captivated both professional astronomers and amateur stargazers with its striking reddish hue and massive size. It serves as a majestic beacon in the constellation Orion, easily spotted with the naked eye from Earth. Yet, it is not merely its beauty or brightness that has thrust Betelgeuse back into the scientific spotlight. Rather, it is a dramatic and wholly unexpected event that has reignited interest, a staggering 250% increase in brightness recently observed by the James Webb Space Telescope. This sudden surge has sparked an intense wave of excitement and speculation within the astronomical community, with scientists around the world questioning what this unprecedented transformation could mean for the future of this colossal star. Classified as a red supergiant, Betelgeuse is currently in the late stages of its stellar life cycle. Situated approximately 642 light-years from Earth, it is one of the largest and most luminous stars in our galaxy. Its radius is nearly 700 times that of our Sun, and its luminosity exceeds the Sun's by over 10,000 times. As a red supergiant, Betelgeuse is inherently unstable, characterized by erratic cycles of dimming and brightening as it approaches the inevitable end of its life. These cycles are not unusual for stars of this kind, but the scale and speed of Betelgeuse's recent brightening are unlike anything observed before. This extraordinary behavior has opened new frontiers in the study of stellar astrophysics. Thanks to the groundbreaking infrared capabilities of the James Webb Space Telescope, astronomers have been able to penetrate the dense layers of dust and gas that typically obscure Betelgeuse, and capture a clearer view of its surface and surrounding space. What they observed was astonishing. In just a matter of weeks, Betelgeuse's brightness increased dramatically, suggesting that powerful internal forces are at play. Such a surge in brightness points toward a dramatic shift within the star's structure, potentially indicating that Betelgeuse is entering a new, more volatile phase that could lead to its long-predicted end, a supernova explosion. For years, astronomers have speculated that Betelgeuse might go supernova, a cataclysmic event marking the death of a massive star. Traditionally, this was expected to happen within the next 100,000 years. But the recent brightening has prompted some to wonder whether that timeline might be significantly shorter. If Betelgeuse were to explode, it would be an astronomical event of unprecedented magnitude in recorded human history. Its supernova would likely be visible even during the daytime, rivaling the brightness of the full moon and remaining a luminous spectacle in the sky for weeks or even months. Fortunately, despite its sheer scale, Betelgeuse is far enough away that its explosion would pose no threat to Earth. Instead, it would offer scientists a rare opportunity to observe a nearby supernova in real time, a chance to gather data that could redefine our understanding of stellar death and the cosmic forces involved in such transitions. This phenomenon has also revitalized scientific curiosity about red supergiants in general. These stars, due to their vast size and internal complexity, continue to baffle researchers. Betelgeuse, in particular, has been a subject of intense study for its irregular patterns of light variation, which defy many traditional models of stellar behavior. Understanding the cause of its 250% increase in brightness could be key to unlocking deeper insights into the life cycles of similar stars. One emerging hypothesis suggests that Betelgeuse may have experienced a massive convective event, a process in which a bubble of hot gas rises from the star's core to its outer layers. In red supergiants, such convective movements are common, and when these cells reach the surface, they can result in dramatic changes in brightness. If material was violently ejected during such an event, the subsequent exposure of new hot regions could account for the observed spike in luminosity. Another possible explanation is that Betelgeuse recently underwent a stellar eruption, ejecting a substantial amount of mass into space. This expelled gas and dust, when illuminated by the star's intense radiation, could create a cloud that reflects additional light toward Earth, enhancing the star's brightness. This theory aligns with the 2019 dimming episode, when Betelgeuse mysteriously lost much of its visibility, an event many scientists now believe was caused by a dust cloud partially obscuring the star. The current brightening might be a kind of rebound caused by newly ejected material that no longer blocks the light but instead intensifies it. A third and particularly intriguing theory involves Betelgeuse's magnetic field, an aspect of the star that remains poorly understood. Some studies suggest that the magnetic fields of red supergiants could be far more complex and dynamic than previously thought. A sudden change or upheaval in the magnetic structure might influence how energy travels through the star, resulting in significant and rapid shifts in brightness. If the recent surge is linked to such magnetic dynamics, it could mark a turning point in our comprehension of how magnetic fields affect the evolution and death of massive stars. While these hypotheses remain under investigation, one thing is clear: the recent events surrounding Betelgeuse have underscored the critical role that mass loss plays in the final chapters of a red supergiant's life. These stars are known for shedding enormous quantities of material into surrounding space. And this loss not only alters their internal structure, but also contributes to further instability. If Betelgeuse is now shedding mass at an accelerated rate, it could be approaching a critical threshold that signals the final stages before a supernova. The timing of this transformation is especially fortuitous for astrophysics. The James Webb Space Telescope, with its ability to observe at infrared wavelengths, is ideally suited to study stars like Betelgeuse, which are often cloaked in cosmic dust. Its instruments allow scientists to dissect the light emitted by the star, revealing detailed information about its chemical composition, internal structure, and temperature. With Betelgeuse now in such a dynamic state, it provides a unique and timely opportunity for scientists to witness stellar evolution in action. Still, despite the excitement, astronomers caution that a sudden brightening does not guarantee an imminent supernova. Red supergiants are by nature highly unpredictable. Betelgeuse could simply be exhibiting another of its many phases of instability, albeit a particularly intense one. However, a 250% increase in brightness over such a short span is anything but routine, and it suggests that profound changes are indeed taking place within the star. These developments serve as a vivid reminder that the universe is a living, changing place, filled with massive celestial objects that pulse, flare, and erupt with energies beyond our comprehension. Betelgeuse's current state has attracted the attention of observatories across the globe. Space-based platforms like the Hubble Space Telescope and ground-based observatories such as the Very Large Telescope in Chile are now working in concert with JWST to track every fluctuation. Tracking physical changes, scientists are also using Betelgeuse as a vital case study in refining theoretical models. The star's behavior is helping bridge the gap between observational astronomy and complex simulations that attempt to replicate the internal processes of massive stars. When a star like Betelgeuse reaches the end of its fuel supply, particularly when it begins fusing heavier elements such as iron, its core collapses, triggering a violent supernova. Whether Betelgeuse is approaching that final stage remains unknown, but its current behavior is fueling intense international research aimed at making predictions with greater accuracy. Beyond the science, Betelgeuse's transformation has rekindled public fascination with the cosmos. Social media, educational institutions, and science communicators have turned their attention to this celestial drama, captivating global audiences. The idea that a star visible from our own backyards could explode in our lifetime and light up the sky in a dazzling display of cosmic energy feels like something out of mythology. Yet, it is a very real possibility. For millennia, humans have looked up at the stars seeking guidance, meaning, and inspiration. Now, Betelgeuse offers us not just a vision of the heavens, but a chance to witness firsthand the awe-inspiring power of stellar evolution. It has evolved from a twinkling point of light into a living, changing entity whose fate may unfold before our very eyes. This remarkable star reminds us how much we have yet to learn and how every flicker in the sky could be the beginning of a cosmic story that will change the way we understand our universe forever. As Betelgeuse continues to evolve before our eyes, the implications of its transformation stretch far beyond the fate of a single star. It has become a symbol, a cosmic messenger reminding us that the universe is in constant flux and that even the seemingly unchanging stars that have guided sailors, inspired poets, and served as seasonal markers for millennia are not eternal. They are dynamic living systems subject to the same principles of birth, change, and death that govern all matter in the cosmos. The unfolding story of Betelgeuse is thus not only a scientific revelation, but a profound philosophical and existential one as well. In the realm of astrophysics, Betelgeuse is now a case study for virtually every area of stellar research. From the behavior of convective flows in massive stars to the enigmatic nature of magnetic fields, from the mechanics of mass ejection to the formation and evolution of circumstellar dust, it touches on all the mysteries that lie at the heart of understanding how stars live and die. Already, the wealth of data collected in recent years is helping to fine-tune computer simulations that attempt to model the internal mechanics of red supergiants, simulations that until recently relied heavily on theoretical estimates and lacked the kind of real-time observational support that Betelgeuse now provides. One of the central challenges in modeling stars like Betelgeuse is their sheer size and complexity. Unlike smaller, more stable stars such as our Sun, red supergiants are chaotic in their structure with convective cells so large they could span the orbit of Jupiter. These cells churn violently, transporting energy from the core to the surface and giving rise to dramatic fluctuations in brightness and temperature. The material expelled in these processes can form vast shells of gas and dust around the star, further complicating observations and altering the star's visible characteristics depending on our viewing angle. By studying how Betelgeuse's light is filtered through these layers, particularly in infrared wavelengths that penetrate dust, astronomers are learning how to read the subtle signs of internal activity and instability. Moreover, Betelgeuse offers a valuable laboratory for testing theories about nucleosynthesis, the process by which elements are forged in the cores of stars. As a red supergiant fuses heavier and heavier elements, it creates many of the atomic building blocks of life. When it eventually explodes as a supernova, these elements are scattered into space, enriching the interstellar medium and seeding the formation of new stars and planetary systems. In this way, every carbon atom in your body, every molecule of oxygen you breathe, and every speck of iron in your blood owes its existence to a star like Betelgeuse. Watching such a star approach its final act is, in a sense, like watching the source of our own origins, an astronomical mirror that reflects both our past and our destiny. The broader consequences of a Betelgeuse supernova would also extend to multiple scientific disciplines, offering an extraordinary natural experiment that could transform our understanding of the universe. For example, the study of gravitational waves, ripples in spacetime predicted by Einstein's theory of general relativity, could gain vital new data from such an explosion. If Betelgeuse's core collapses into a neutron star or black hole, the process might generate gravitational waves strong enough to be detected by observatories like LIGO or Virgo. Such an event would offer an unprecedented cross-check between electromagnetic observations and gravitational wave data, linking what we see in light with the distortions of space itself. This synergy could refine our models of core collapse supernovae and illuminate the nature of extreme matter states that are otherwise unreachable in laboratories on Earth. Moreover, a nearby supernova would also shed light on the origins and acceleration mechanisms of cosmic rays, high-energy particles that constantly bombard Earth, yet remain among astrophysics' longest-standing mysteries. Despite decades of study, scientists are still uncertain about the specific sources and processes that give cosmic rays their incredible energies. A Betelgeuse supernova would let us observe in real time the birth and propagation of these particles in our cosmic neighborhood, potentially solving puzzles that have persisted for generations. The proximity of Betelgeuse would make it an especially rich target for these investigations, offering levels of detail impossible for more distant supernovae. Beyond these purely scientific benefits, the attention focused on Betelgeuse is driving significant improvements in observational technologies and data analysis methods. Instruments that rely on adaptive optics are being refined to handle the turbulent, ever-changing surfaces of red supergiants, allowing for sharper and more detailed imagery despite Earth's atmospheric distortions. Astronomers are developing new algorithms to integrate data across the entire electromagnetic spectrum, from radio to X-rays, creating richer, more cohesive portraits of stars like Betelgeuse. Machine learning techniques are also being harnessed to analyze its light curves and spectral variations, training artificial intelligence systems to identify subtle patterns and make predictions about future changes. In many ways, Betelgeuse has become a proving ground for the next generation of astronomical tools, catalyzing innovation that will benefit the study of countless other celestial objects. Educationally and culturally, the renewed interest in Betelgeuse is proving invaluable. Schools and universities are weaving its real-time story into science curricula, using it as a vivid example of how scientific knowledge evolves, not as a static collection of facts, but as a dynamic, unfolding process. Students are learning not just the physics of stellar evolution, but the mindset of inquiry, how to ask the right questions, design observations, test hypotheses, and adapt to new evidence.